AB Calculus 5.1, day number 1, antiderivatives. Okay, here we are, second semester. Everything we've known to this point has been derivative or limit related. We are about to reverse that operation and start talking about anti-differentiation, which undoes or reverses the process of differentiation. So given a function f of x, we will look for an antiderivative, which we'll call capital F of x, whose derivative is f of x. Okay, so if you look at the notation here, the derivative of the function we're seeking is the function we have. Or we could say that capital F prime of x is equal to f of x. So you have to reverse your thinking. We're used to thinking f of x is x, therefore its derivative, f prime of x, would be 1. Now what we want to think of is a function, capital F of x, whose derivative is x. So you want to just kind of get into the mode of thinking about a derivative whose function is the one you have. Okay, so now as I look at each of these, A, B, C, D, and E, right, I can see that there's going to be a pattern. Right, I'm going to add now, instead of using the power rule that we're used to using in differentiation, we're going to find the antiderivative by doing the opposite of that power rule to some extent. So you can see that the antiderivative of x would be x squared over 2. The antiderivative of x squared would be x cubed over 3. The antiderivative of x cubed is x to the 4th over 4. So the antiderivative of x to the nth will be x to the n plus 1th over n plus 1. Now I am missing one thing. I have to tag each of these with a general constant of integration, is what we call it. The reason why is because any one of those could have a constant attached to it, and when you take its derivative, it falls off, right? The derivative of a constant is 0. So please make sure and include in your general antiderivative this value c. And it doesn't matter what it is. Eventually, we'll come up with how to determine the specific value for that constant. Okay, so by definition, a function f is an antiderivative of little f on an interval, provided that big F prime is equal to f of x for all x on that interval. So you can see the family of antiderivatives here. Notice that, right, each of these curves, though it has a different constant added to it, would have the same slope at each of the appropriate x values. Right, so let's for example look at, looks like this x value, let's say at x1. Right, each of the slopes on each of the curves, regardless of its vertical shift, right, its vertical shift being, these values C1 through C5, has the exact same slope. Therefore, again, when we add the c, it adds a family of potential functions. Likewise, over here in this linear expression, right, you can see that the slope of a linear function is going to be the same throughout, regardless of whatever the y-intercept is. Right here, -3, -1, 2, 3.5, etc. Okay, so understand that we're finding an antiderivative and adding some general constant to the end of it. All right, let's look at a few examples. Okay, example 2. Use what you know about derivatives to find the following antiderivatives. Okay, if I know that f of x equals 3x squared, I'm going to make a guess here and say, and some of this at first will be guessing, or it'll be a quick recognition of some property that you're aware of. Okay, but in this case, I would say, how about x cubed? And we'll add, of course, our constant of integration. Now, how could I be sure that f prime is equal to f of x. Big F prime is equal to f of x. Well, I could take the derivative with respect to x of x cubed plus c. Let's see what we get. We get 3x squared. And now I have verified, right, through this process that little f of x is actually equal to 3x squared. Therefore, big F of x, or the antiderivative of little f of x, would be x cubed plus c. Okay, I'm going to make a hypothesis here that big F of x in part B is going to be the inverse tangent of x plus c. I will confirm it by taking the derivative of the inverse tangent of x plus c. Of course, the c will drop, and the derivative of inverse tangent is 1 over 1 plus x squared. Okay, now everything over here, the verification of it, is not necessary for full credit. If you truly understand your antiderivatives, then you're good to go, provided you don't goof something up with signs, right? So, for example, very common here in part C, someone will say that big F of x is going to be cosine of x plus c. And that's actually incorrect, because the derivative with respect to x of cosine x plus c is equal to negative sine x. So what I want to do is I want to change the sign of cosine, and I get my antiderivative. Okay, tricky one here in part D. Not tricky if you remember your rules. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent of x plus c. All right, let's look at a little bit of notation work here. We know that d dx of f means find the derivative of f with respect to x. We need a notation that means find the antiderivative of f. The notation we use is called the indefinite integral, and it looks like this. All right, so we know that d dx of f is equal to the derivative of f with respect to x. But how do we go the other way? Well, the integral of f with respect to x, all right, so this is the indefinite integral. And when you have an indefinite integral, which means you don't have a number here and a number here, right? Limits, which we're going to talk about later. But if the integral notation is absent of any values at the upper and lower index of that symbol, it kind of looks like a big S, then it's called an indefinite integral. Okay, with respect to x is the dx. Right? That means with respect to x. Okay, when that's present, that's telling us to find big F. Now, when you have an indefinite integral, you'll always end up with a constant of integration. If you don't have an indefinite integral, which is called a definite integral, which we are not going to talk about until later this chapter, but a definite integral could be like the integral from 2 to 5 of f of x dx. Then you will not have that constant of integration. We'll talk about that more later. That's beyond us at this point. So for the examples we saw above, instead of writing out, find the antiderivative of each of the following, this mathematical notation tells us to do exactly what we were told above. So we would have x cubed plus c. We would have inverse tangent of x plus c. We would have negative cosine of x plus c. And we would have the tangent of x plus c. So a nice compact notation telling us how to operate within the world of derivatives and antiderivatives. Okay, let's look at a few more examples. Okay, let's look at 3 rules that are commonly seen within the world of indefinite integrals. First is the power rule. We already actually talked about this a little bit on the first slide, but to find the integral of a power function, right, like x to the p, we would take and add to the exponent and divide by that value. And of course, add our constant of integration. Okay, for the constant multiple rule, anytime you have a constant c, I typically like to pull it out in front and then go ahead and work my antiderivative or my integral expression from there, which of course would be c times big F of x plus, and this, I don't really necessarily like this value here. Let's call this a, because it's going to start to confuse. Okay, but we get something like that. Okay, that's the constant multiple rule. Now the sum rule, also very helpful in that you could have a pretty complex function if you have the sum of two functions. So you're allowed to use the sum rule, or difference rule for that matter. So this could be plus or minus. Take the integral of each of those functions separately with respect to x. So we would get something like big F of x plus or minus big G of x. And then I would combine their constants of integration into just one value c. So instead of like f of x having plus some value c1 and g of x having plus some value c2, we just combine those two into some general value c. Okay, so that's going to be the sum, and I should really put difference rule. Okay, so let's look at using these rules to find the following antiderivatives. So if I want the antiderivative of f of x, okay, I would write the integral, indefinite integral of 3x squared with respect to x. I'm going to use the difference rule, sum or difference rule. And actually I'm going to, in a moment, I guess I could do it in a moment, 10x dx minus the integral of 7 dx. Now I'm also going to use the constant rule. I'm going to pull that 3 out in front, just work with x squared. Pull out the 10, just work with x. And I'll leave the last integral expression as minus 7 dx. So this will be 3 times x cubed over 3. I'm using the power rule there. Now I'm gonna tag all of the constants because I'd get 3 constants of integration. I'm gonna tag it on at the very end. Okay, and then I'm going to have minus 10, and that'll be times x squared over 2, and then minus 7 times x, okay, and then plus c. So I'll have to regroup here, erase that, and then simplify. Therefore, the integral of f of x dx ends up equaling x cubed. I'm just simplifying, 3's reduce. That becomes a negative 5, okay, minus 5x squared, minus 7x, and plus c. If I were to take the derivative of this, I should end up with the original function f of x. Okay, part B, let's take the integral of, and let's use the sum rule here as well as some properties of exponents. That would be x to the negative third plus 6 times the integral of x to the negative 7th. Now, as we work through these, you want to be very careful with your exponents. So recall that we are going to add 1 to that and divide by that new number. So this would be x to the negative 2 over negative 2 plus 6 times x to the negative 6 over negative 6 plus c. So what we would get is negative 1 over 2x squared minus, I'll reduce these, 1 over x to the 6th plus c. Let's see if we get the correct antiderivative here, or if I goofed something up. So I'm going to write this as negative 1 over 2x to the negative 2 minus x to the negative 6. Okay, so using the power rule of differentiation, I'd bring this negative 2 down in front, which would not only make the term positive, but would also reduce the 2's. And then that would bring our term to an x to the negative 3. Then I bring the negative 6 down in front, which makes this a positive 6x to the negative 7th. And if I rewrite that, I get 1 over x cubed plus 6 over x to the 7th. And it looks like that matches f of x from the original. Therefore, I did it right. I didn't goof it up. I got my mindset right. Get your mind right, and you'll be just fine. All right, let's look at one more slide of examples. Okay, letter C. Let's take a look at letter C. I'm actually going to do a quick reduction. I'm going to reduce each of the terms by x to the 5th. That'll make the first term 4x. That'll make the second term 3. And that'll make the third term negative 8x to the negative 5th. So I'm putting this in a form. I don't want it in this rational form. I'm going to put it in a form that's useful for me. So again, I'm going to set up the integral notation. So the integral of f of x dx is equal to 4 times the integral of x dx plus the integral of 3 dx minus 8 times the integral of x to the negative 5th dx. Okay, this will equal 4x squared over 2 plus 3x minus 8x to the, we're going to add 1, negative 4th over negative 4 plus c. All right, let's go ahead and bring our work over here. I'm going to reduce. That gives me 2x squared. That was not my best 2. Let's try that again. Plus 3x. And this will be plus, right, I got a negative 8 over negative 4, 2x to the negative 4th plus c. Don't forget the plus c. I'm going to rewrite this in a form that's a little bit nicer to me. And there you have it. All right, so let's move on to part D. In order to integrate part D, we're going to have to actually expand it. So let's expand this expression. This will be y to the 4th plus 8y cubed plus 16y squared. I believe I expanded that correctly. Let me check. Y squared plus 4y, y squared plus 4y. That'll be y to the 4th plus 4y cubed plus 4y cubed plus 16y squared. Yeah, that works out. Okay, so now let's work this. Now notice we're integrating with respect to y now. No big deal. Nothing changes, just a different letter. Okay, so the integral, in this case, let me rewrite. Integral of y to the 4th dy plus 8 times the integral of y cubed dy plus 16 times the integral of y squared dy. All right, that will equal y to the 5th over 5 plus 8y to the 4th over 4 plus 16y to the 3rd over 3 plus c. Let's see if we can simplify any of that. Y to the 5th over 5, no change. Let's write this as a 2y to the 4th plus a 16y cubed over 3 and plus c. There's our antiderivative of the original expression. Okay, last example. You can see you have a fractional exponent here. All right, so let's just bring the 3 out in front to limit any confusion and use this rational exponent in order to integrate. All right, so I'm going to add 1 to my exponent. So I'm going to take 2/3 and I'm going to add 3/3. So that gives me x to the 5/3. And of course, I want to divide by that same value, 5/3. Now, fractions can become annoying. Dividing by 5/3 is the same as multiplying by 3/5. So this is really 3/5 times 3 times x to the 5/3. Don't forget plus c. Okay, so let's write this as 9/5 x to the 5/3 plus c. Now, I want to confirm that this is true. So I'm going to quick take the derivative with respect to x of 9/5 x to the 5/3 plus c. I know the c is going to drop off, so let's multiply 5/3 times 9/5 times x to the x to the, I'm using the power rule, so I got to subtract 1 from 5/3, which leaves me with 2/3. Okay, so I like the x to the 2/3, that matches up. And you can see that the 5's reduce and the 9 and the 3 reduce, giving me 3x to the 2/3. So I've confirmed, right, check, that this right here is the correct antiderivative of the original function. All right, guys, that is 5.1, day number 1. We'll see you in the next video.